Thank you for, I forgot again. Thank you. Okay, homework 7. Homework 7. Okay.
Okay, so for the first one, so we had a symmetric columns that you showed already, like balanced. Now we have 8 rebars. So could you please explain, or do you have any example for similar to this one? So how we are going to do the calculations based on
Yes. No,
also.
no. I have an example in the lecture before the last lecture. The very first lecture that I did on column design, we did exactly this. We calculated P naught, Pn, and phi Pm.
Right, but that time you had like 8 rebars for each side. And is there any difference than we have like at the middle we have 2 rebars? Is there any difference between them? No, right? So
Not if you don't have any moments, then it doesn't matter where the steel is. And this one does not have any applied moment to it.
oh, okay, yeah, okay, so pure compression. Okay.
That's right.
Uh,
And problem number 2 is also pure compression. There's no moment applied to that either.
okay. Um, like generally, what about the third question?
Okay. Yes.
Okay, so could you please, so basically you are telling us we have 0.001 and 0.003 is compression, 0.001 is tension.
No, it's not. 001 is still compression.
Okay. Okay.
So you have 003 on the one side in compression. You have 001. That's not the steel. That's the extreme fiber of concrete. That's 001. But look at the diagram. It doesn't go through the neutral axis. So that's not tension. That's 001 compression. So what I've done, when we go through the examples, and I did the example of doing the interaction equation, and we did 5 points.
Right.
Well, this homework assignment is just asking you to do 1 point, one specific point, instead of 5 points.
Got it. First is pure compression, and this one less than. I think this is.
This one is a little different than the 5 points I did in the example, but you should be able to take this strain diagram and follow the methodology that I did for one of those 5 points. And so what I'm saying is this is like a 6th point. This is not exactly the same as any of the 5 points that I did, but you should be able to follow how I did those 5 points and do the same thing for this.
Okay. All right. Thank you so much.
Okay. Does anybody else have any questions for me?
Question real quick, Professor, about when you mentioned MATLAB, would you say, like, from a professional standpoint, that that's almost a requirement if let's say I want to practice structural engineering in the future?
Great question. It's actually quite the opposite. I have not met any other structural engineers that use MATLAB. None. Nobody knows what I'm talking about unless they used it in college. So no, MATLAB is like almost non-existent in the PTSD. Good one. In the world of structural engineering, it's almost non-existent. And that's because so much of what structural engineers do, somebody makes a software package to help them do what they do. It's only when you do things that 99% of the general population does not do that you need like custom solutions. And I guess I went to MATLAB only when I was trying to do data manipulation in Excel, and I had so many data points. I mean, like hundreds of thousands of data points that Excel just kept crashing and dumping on me, that I moved over to MATLAB, because MATLAB can handle huge arrays and huge reams of data without even breaking a sweat, whereas Excel is dying over the same data. But the data that I'm creating is really from either digital or real world experimentation, testing, things like that. Just doing stuff that's like more advanced and more theoretical than what most practicing structural engineers would have to deal with in their everyday design world. Does that make sense?
Yeah, understood. I thought like we would have to like have a little bit of practice in MATLAB, but that's good to know that it's almost in your perspective non-existent.
Non-existent. It really is. If most structural engineers want to create a template or do something, their own thing that nobody has made software for, like just for example, throw it out there. Say like you do concrete moment frames a lot. Say like you do a lot of jobs and you end up doing a lot of concrete moment frames. And you want to simplify your calculations so that you're not rewriting and redoing the same thing over and over and over, then you would create a template. And that's fantastic. A lot of us create templates. But for most applications, Excel is just fine. The functionality of Excel lends itself to creating templates just fine. It's only when you do, like I said, testing, like I showed you guys the shear testing that I did a couple weeks ago, and we got a lot of data from that. Or you do more theoretical stuff, like simulating. I did a project one time where we took concrete columns that are fixed to a foundation only. They weren't tied into the building yet at all. They're just sticks standing out in the field, bolted to a foundation. What happens if you hit them with an earthquake? And I was doing more real world, what would you call it? Time step style earthquake analysis. So instead of the equations that the code gives you, which are really kind of simple, I used real world data. So I downloaded seismic records from like 30 different earthquakes, and then I plugged those into a nonlinear finite element program called OpenSeas and ran it through that so that I got a real like plastic hinging behavior and yielding behavior, all kinds of really interesting things. And then all the data from the OpenSeas runs was like hundreds of thousands of data points and numbers. And you can't make any sense out of it. And it killed Excel. Excel just died a miserable death trying to process all the data. So that's where MATLAB really came into its own. But most engineers don't do stuff like that.
Okay, cool. Thank you.
Okay. Let's, unless there's any other questions. Okay, let's continue. Let's see, I got my textbook. We're gonna need our textbooks today. All right, so now what we did last time was we calculated interaction diagrams by crunching through at least 5 design points and then basically connecting the dots to form like a rudimentary segmented interaction diagram that then we can plug in our loads and see if the column works. There are design aids. And so I'm going to show you quickly how to use design aids instead of calculating through 5 interaction points. So to use the design aids, if you go to your textbook and Appendix A, where all the tables are, And what they've done in Appendix A is they reprinted some of the charts from the ACI. Old ACI. ACI doesn't have these anymore. So the charts start on page 619, and it's called graph 2. That's where they start. And then you have graph 3, graph 4. So if you turn to those graphs, you'll kind of see what I'm talking about. And the graphs kind of look like contoured or overlaid interaction diagrams, which is really kind of what they are. But in order to use the charts, we have to create these parameters, K sub n and R sub n. K sub n is equal to P sub n divided by F prime C AG, where P sub n is equal to Pu, your factored axial load, divided by phi. And R sub n is equal to Pn times E over F prime C AG H. Or since Pn is equal to E, that'd be the same as Mn over F prime C AG H. This definition of Rn, however, is different than the one we use for beam design. It's similar, but it's not the same. And of course, Mn is equal to Mu divided by phi. Okay, so let's do an example. If I have a 16 by 16 column where the rebar is located at 2.5 inches off of each face, and I have 4,000 PSI concrete, it's a tied column. Rebar is 60 KSI, Pu is 400 kips, Mu is 200 kip feet. And what's required is we're going to repeat example 1 where we did that whole interaction diagram, only we're going to use Appendix A to find the required steel. So Kn is Pn over F prime C Ag. So if I take 400 kips divided by, and you always assume that phi is going to be the worst. You know it's going to be 0.65. So 400 divided by 0.65 is 615.4 kips. So Kn is equal to 615.4 over 4 times 16 times 16 is 0.601. Rn is Pne over F prime C AGH. E is Mu over Pu, which is 6 inches. So Rn is equal to 615.4 times 6 inches divided by 4,000 KSI. Ag is 16 by 16 and H is 16. H is in the direction, you assume the load's going this way. And that gives me 0.225. Gamma, okay, if you look on your graph 2, at the very top of the chart, you see where it says interaction diagram. F prime C, the one I'm looking at is on page 619. So F prime C equals 4 KSI, Fy equals 60 KSI, gamma equals 0.6. So what gamma is the ratio of the distance between the rebar to the distance of the whole face of the width. So the distance between the rebar is 16 minus 2.5 minus 2.5 divided by the whole width of the beam is 16. I get 0.69. So you notice that on page 619, gamma is 0.6. On page 620, gamma is 0.7. So 0.69 is pretty darn close to 0.7, especially for these purposes. So we're going to use graph 3 on page 620. And from that graph, if I go up the vertical axis to 0.6, and I go across on the horizontal axis to 0.225, which is halfway between 0.2 and 0.25, and I run my finger up there, you'll see that I get a row of 0.34. So I interpolated it. Yeah, right about there. So you kind of have to eyeball it. I mean, if you wanted to write in your book, you could use a pencil and interpolate it better. But I got a rho of 0.034. Okay, so everybody at least see the figure that I'm looking at? Does anybody see the figure that I'm looking at?
Yes, professional following.
Okay. So if rho is equal to 0.034, as it says in this graph number 3, then my area steel is going to be rho times my gross area. So 0.034 times 16 times 16 gives me 8.7 inches squared. I'm going to choose 6 number 11s. Yes, I know there's 8 green dots, but that's just symbolic. 6 number 11s gives me 9.36 inches squared. And I was wondering if I did that. So here's how I got 0.034. There's my 0.6. There's my 0.225. I drew a line that's roughly perpendicular to the contours, and I eyeballed it. So this contour is 0.03. This contour is 0.04. And so it's right in there. That's how I got to 0.034. Notice that the contours go from 1% to 8%. And that's because, according to ACI, your column design has to be at least 1%, but it cannot be more than 8%. So they've covered every percentage between those two. Okay, and then I verified. This is my 6 number 11s that I checked. I ran it on my SP column, the software I just showed you. And when I put my 400 and 200 kit feet in here, that's where it lands. And it clearly does work. It's inside of my interaction diagram. So 6 number 11s works. Okay, so that's the design aids. That's how you use those. Okay, column shear. So equation, or excuse me, ACI 318, equation 22561 can be used, but it is conservative for columns with axial load. So this equation, the 22561, that was when we did shear for beams 2 square root F prime C BWD. And that's the equation that we use conservatively for beams. For columns, that's very conservative because the crushing effect or the load of the column coming down really helps with your shear strength. Okay, so we're going to use this equation instead. Equation 22551, where it kind of looks the same. Here's your 2 lambda square root BWD, but we have this other term in here where NU is the compressive load on the column in pounds divided by 2,000 times the area of the column. So if this is, say, 1, then 1 plus 1 is 2. So then you get twice as much shear strength if this ends up being 2 inside the bracket. So you can see that this is a much more efficient way to use shear for a column than just the old beam shear 2 square root F prime C. ACI 318 table 22561 offers an even more detailed method for calculating VC for columns with compressive loads. So you can use the lesser of A or B, and this is starting to get a lot more complex, as you can see. But 1.9 square root F prime C plus 2,500 times rho times VU over D divided by MU minus NU for H minus D over 8. This is only applicable, though, if this term here is less than 0. If this term is not less than 0, I'm sorry, opposite. If this is less than 0, don't use it. If mu is greater than this term, then you can use this equation, where Nu is the axial load in pounds and is positive for compression. Okay, any questions on that? All right, so if I have an 18 by 24 column, D is 15.5 inches, B is 24 inches. I'm looking at shear going up and down the page. F prime C is 5,000 PSI. Fy is 60 KSI. Pu is 400, Mu is 200 kip feet. I know I don't get very imaginative about these things. But if I have a shear load of 125 kips on this thing, if I use number 4 grade 60 ties, what spacing do I need to put them at? So this is one number 4 grade 60 tie. As I explained before, this is not California. You couldn't build this column in California. But given that this is anywhere else in the world other than California, based on this information, what's the required spacing for these number 4 ties? If you use the simplified equation 22561, or if you use table 22561. Solution. So we need to find the capacity of the concrete alone, VC. So VC is 2, 1 plus Nu over 2000 AG lambda square root F prime C BWD. So we're going to use 2, 1 plus, okay, the axial load, factored axial load is 400 kips. That's 400,000 pounds divided by 2,000 times the gross area is 24 times 18. If I do not say anything different, always assume the concrete is normal weight concrete. So lambda would be equal to 1. Square root F prime C, so square root of 5,000 times BW is 24 times D is 15.5. That all works out to be 77 kips. So then my spacing required is equal to AV FY D over VS. VS is equal to VU minus VVC over phi. So I can plug in, I have 2 legs, 1, 2. 2 legs resisting this shear. So 2 times the area of a number 4 is 0.2, 60 KSI, D is 15.5, VU is 125 is given here, and phi VC is 0.75 times 77, all divided by phi of 0.75, and you get 4.15 inches. So use number 4s at 4 inches on center. Phi VN is equal to phi VC plus phi VS. So phi VN is 0.75 times 77 plus 0.75 times 2. Area of a number 4, 60 KSI. D is 15.5. My chosen spacing is 4. And I get 127.5, which is greater than 125. Okay. Can't say this enough times. Well, maybe you think I can, but I'll say it anyway. When you get to this point, you as the designer have made a choice. You said, I can't space them any more than 4.15 inches apart, so I'm going to put them at 4 inches on center. That's your choice as the designer. After you have made your choice, you must do these last 2 steps. You must calculate what phi VN is based on your choice, not based on some minimum, based on your choice, and then show that your choice leads to a capacity that is greater than the demand. Again, cannot overstress this. This is the most important check right here. All of this gets you to a point where you can make a choice. once you make a choice, you always have to check that choice to make sure that it still works. Okay, what if we use table 22561? All right, so VC now is equal to 1.9 lambda square root of f prime C, 2500 rho W VUD over MU minus NU 4H minus D over 8. Not applicable if MU is greater than this term. So let's calculate this term. MU is 200 kip feet times 12 to get to inch kips, minus NU is 400 kips times 4 times 18 is the height in this direction, minus D is 15.5 over 8. All of that equals minus 425 kip inch. So we can't use equation A. This whole term is less than 0. So equation A is not applicable. Equation B. Here we have 3.5 lambda square root f prime C BWD 1 plus NU over 500 AG. And I plug in all my pertinent values. Lambda's 1, 5,000 PSI, 24, 15.5, 400,000 over 500 AG. This equals 155.5 kips. So my required spacing of AV FYT D over VS now becomes 2 times 2 legs times 60 times D over 125 minus 0.75 times the 155 now. There's your difference. Divided by 0.75, that gives me 33 inches. So the maximum spacing is D over 2, which is 7 3/4. So we're going to end up using number 4s at 6. But look at this crazy difference. We went from 4.15 inches to 33 inches just based on using the more sophisticated equation. I do my back check. V times VC plus V times VS equals 163.1, greater than 125. So we're good. Okay, any questions on lecture 11? All right, and let's go to lecture 12. Okay, so lecture 12, tonight's lecture, is all about slender columns. So a long slender member carrying compressive load is known as a slender column. Okay, so let me get a quick poll. Who here tonight remembers column buckling from mechanics of materials? Okay. Column buckling, mechanics, ringing any bells? You guys shy or you've never had this? Is there anybody still listening?
No, yeah, of course we took it.
We're probably just haven't used it. That's what we're quiet.
Yeah, like before.
but you know what I'm talking about. You've had the concept, right?
Oh yeah, the concept, too much lateral force, which makes the height wise just kind of just cripple sideways.
Okay,
Sort of.
that's fine. That's a good enough explanation. Euler, yes, my man, Euler.
There we go there.
All right. Okay. Well, that's where we're starting from. That's tonight's lecture, is how do we deal with slender columns in the world of concrete? Every material has to deal with slender columns. Steel, timber, even masonry, I guess you could make pilasters that are slender. But in the world of reinforced concrete, we have some specific ways that we deal with the slender column problem. So that's what we're doing tonight. So if we start with a pin-pin supported column of an unbraced length L sub U, this is the terminology that our code uses. L sub U is the unbraced length of a column. So if we start with an unbraced length, if we add a factored load PU, okay, so here's the factored load going through the middle of the column, and we have factored moments M1 and M2 as shown, where M2 is the larger of the two moments, then we get the following axial load and moment diagrams. The axial diagram looks like this, where you have a constant PU factored axial load, and the moment diagram looks like this, where M2 is greater than M1. The applied moments, you're basically twisting the column. The applied moments cause a column deflection as shown, right? So if you try to twist the column here and here, you're going to bend that column and it's going to deflect as shown. So if I label that deflection delta, the axial load now has an eccentricity at the midspan of the column equal to delta. That eccentricity produces an additional moment equal to P delta. So here's the moment diagram due to just P delta. There's no delta at the end of the column, so the extra moment is 0. Delta is maximum at the middle of the column, so you have a maximum additional moment, and it's 0 at the other end. This additional moment adds directly to the original applied moments M1 and M2, like so. So originally it was just a straight line. Now it's bulged out. You have more moment now at the midspan than you did at either M1 or M2 originally. The combined moment MU then produces even greater deflections, which in turn create greater moments. Depending on the degree of slenderness and the magnitude of the original moments M1 and M2, this cycle either will converge to a stable answer or it will prove to be unstable. Unstable means it collapses, it fails. ACI 318, section 6645 for non-sway and section 6646 for sway columns eliminates this iteration process by introducing the moment magnification method. So the code simplified it quite a bit so that we don't have to calculate exactly what this P delta moment is, add it to the original moment, recalculate it, find what the new P delta is, find what the new moment is, and just keep iterating into oblivion, trying to figure out where this thing stabilizes. The code gives us a closed loop solution process instead of an open iterative process. Moment magnifier method uses a factor delta to amplify the M2 moment to a final design moment M sub U. Okay, unbraced length. Critical to a column slenderness ratio is the unbraced length. Typical concrete columns are braced against buckling at each floor line. The unsupported column length L sub u is the height of the column from the top of the floor below to the underside of the supporting slab, beam, or column capital above. Depending on support conditions, there may be different unsupported column lengths in each coordinate direction. So you could have something that braces a column only north-south, but it's not braced east or west. You have to be careful about that. Effective length factors. We invented a K factor. K factor is introduced to create an effective length of column when the support conditions other than pin-pin might exist. If the columns are braced or non-sway, K is going to be something less than or equal to 1. If the columns are unbraced or sway columns, then K is going to be something greater than 1. Here's some examples. For a pin-pin condition, then K is exactly equal to 1. It's exactly 1 sine wave is the shape of the deflected shape. So this is what Euler was thinking of when he derived Euler's buckling load. It was this shape that he had in mind when he created that equation. But we need to modify that equation if we have something other than pin-pin. If we have fixed-fix, then K is going to be equal to half, because the fixity doesn't allow this to rotate, and the actual half sine shape is about half the length of the total length. So K is equal to 0.5. So K theoretically is exactly half of your clear height. However, there's a K suggested, because nothing in the world of construction is ever perfect. So you might consider using a K factor of 0.65 instead of 0.5 to account for construction. Because some support conditions are difficult to develop in a real structure, suggested values for K might need to be more conservative. Basically what I just said. If you have fixed pin, then theoretically you have a 0.7 effective length, and it's suggested maybe use a 0.8. Brace frame columns can always conservatively use K equal to 1 without further analysis. So if you're not sure exactly what you have, if that column's braced, you can always use 1. 1 is always conservative. Okay, now if we move over to unbraced or sway columns, if you have a column that is fixed in terms that it can't rotate, but it can translate, if it can sway over, then this is a fixed side sway condition. And K theoretically is 1, because it's still 1 sine wave, but it's suggested that you use a 1.2 factor there. If you have a pinned fixed, but that allows sway, so a fixed pin side sway condition, K is theoretically 2, and you can go ahead and use 2 for that. And if you have fixed free, for a fixed free condition, K is theoretically 2, you can use a suggested 2.1. Okay, braced or unbraced. If you have a frame like this frame here, but this frame is being laterally supported by a bracing element, a shear wall, a moment frame, something to that effect, so that the lateral stability of the building does not rely on the stiffness of these columns. It's relying on this wall. Then you have a braced frame. And when you apply load to this braced frame, it takes on a shape that looks like this. If, however, you do not have a supporting bracing element, like here, so all you have is this bent frame, and if there's any side sway, the side sway is being resisted by the columns themselves, not by something else. If this is what you have, then what you have is an unbraced frame. This is the deflected shape of an unbraced frame. So not only do you have, bending in the beam, but you have this side sway deflection of the columns themselves. ACI 318 presents several tests for braced or unbraced criteria. ACI 318.625 says that if a bracing element has a stiffness of at least 12 times the gross stiffness of all columns in that story, then those columns are braced. So here, this shear wall would be many times more than 12 times stiffer than these spindly little columns here. ACI 6643 offers two tests. The increase in column end moments due to second order effects does not exceed 5% of the first order moments, or Q in accordance with 66441 does not exceed 0.005, where Q is equal to the sum of all the axial loads times this deformation divided by the shear times the story height. First order relative lateral deflection, height of the story. Okay, so this is really just kind of FYI. I'm not going to really dig into it too deeply. We don't really use this very much. In practice, most of these tests are not necessary. It will be obvious which columns are braced and or unbraced. So let me go back here real quick. Okay, looking at this situation, it's like, duh, that's braced. And double duh, that's not braced. See what I mean? So the code has some defined criteria, but we hardly ever look at it. We just look at the structure and say, well, it's got a shear wall. These columns aren't doing anything laterally. Or, oh, there is no shear wall, brace frame or moment frame. These columns are on their own. So it's usually pretty clear. Okay, any questions on that? In lieu of using the K values from the figures given above, a more accurate answer can be found from using what we call alignment charts. ACI 318 figure R stands for reference, so that's in the commentary. So R625A can be used for non-sway, and R625B can be used for sway columns to find the value of K. Each of these charts uses a psi value, psi A at the top and psi B for the bottom of the column, where psi is equal to the sum of EI for the column divided by the length of the column over the sum of E times I of the beam divided by the length of the beam. So the top is sum of the stiffnesses of the columns, including the column being designed, and the bottom is the sum of the stiffnesses of the beams framing into the joint in plane in the direction of interest. LC is center of joint to center of joint of the column. L is the center of joint to center of joint of the beam. Psi is equal to infinity for a pinned condition, but usually just taken as 10 because that's more conservative. And psi is equal to 0 for a fixed condition, but usually taken as 1 because that's more conservative. For the psi equation, there are several choices for the moment of inertia of the columns and beams. For laterally supported structures, ACI 318.66312 allows for the simplest version where I is equal to half of I gross. But in the psi equation, the half factor would divide out, and so this equation really isn't applicable for this application. Okay, so what else do we got? ACI 318.66311 offers a bit more realistic values for the moment of inertia. Table 66311A offers that you use 70% of I gross for the column and you use only 35% of I gross for the beams. Why would you use more of the moment of inertia for a column than the beam, you think? Any ideas? What happens to a beam when you put it into service? What do beams do when you put them into service?
They hold they hold they hold self weight and whatever is going on top of it.
They do, but because they're in flexure, what would you expect to happen to a beam when you put the load on them?
Have a deflection.
It would have a deflection, and
Mm,
what does concrete do?
correct.
Yes, concrete cracks. That's
Okay.
right. So beams, and we just had a lecture on that. I think you had a homework on that where you calculate I cracked and I effective because beams crack. Well, because beams crack, their moment of inertia is reduced. Columns crack as well, but with all that compression on the columns, the cracks don't form nearly as deeply because you have all that compression holding the cracks down, kind of squishing all the cracks together. So columns do not degrade nearly as fast as beams do in their stiffness. That's why columns are at 70% and beams are only at 35%. Does that make sense?
Yeah, for sure. I mean, I want to say that the columns do mostly compression and the
Yes,
beams do more tension than the columns. They bend.
exactly right. Yep. Okay, so we have to use something to make a guesstimate because we got to use this equation. And in this equation is I for the column and I for the beam. So what we're going to use is 70% of the gross moment of inertia for I of the column and 35% of the gross moment of inertia for I of the beam. Additionally, ACI 318-66311 prescribes to divide the column moment of inertia by a factor of 1 plus beta ds, where beta ds is the ratio of sustained shear to the total shear in that story. However, we rarely ever do this because the sustained component of story shear, usually you don't have any sustained story shear because usually lateral load is transient. Usually lateral load is wind or seismic, and those are transient. They only last for seconds. So usually beta ds is equal to 1 because the ratio of the sustained shear to the total, actually, I'm sorry, beta ds is usually equal to 0 because the sustained shear is none of the total shear. Okay, but the code makes us look at it, but beta ds is usually equal to 0. Okay. Alternatively, ACI 318-66311 and table 66311 give more accurate values for the moment of inertia, where we can calculate this rather cumbersome equation that has to be equal to or greater than 35% of I gross, but less than 7/8 of I gross. So this, if you needed a more accurate value for the gross moment of inertia, you'd use this equation here. For beams, you use this equation here, which is between 25 and 50%. of I gross. There's times when you might need a little more precision, but usually just using 70% and 35% is good enough. Okay, so you can use these if you need to, but it's a lot easier to just use 35% and 70%. Where a column bears onto a concrete footing, we have a different procedure for determining psi. Psi at a footing is equal to the 4 times E times I of the column divided by L of the column divided by I of the footing times this case of S factor, where IF is the moment of inertia of the footing in inches to the 4th, in plan view in the direction in question, and case of S is a coefficient of subgrade reaction. It's a measure of soil stiffness. The units are KSI over inch. And this appears in the PCI Design Handbook, Precast Concrete Institute Design Handbook. You can find this in a number of places, but it's just a kind of a rule of thumb type of thing where you plug in your allowable soil pressure and you use that to find this subgrade modulus that is measured in PSI per inch or KSI per inch. Can be approximated from the allowable soil pressure given in typical soils report. For the purposes of this class, you can assume that case of S is equal to 0.120 KSI per inch or 120 PSI per inch for the purposes of this class. And the alignment chart itself is figure R625 on page 65 of ACI 318 code, as well as figure 11.3 on page 317 of your textbook. It's in both places. So it looks like this. Okay, let's see. Let's do the example and then we'll take a break. So for example 1, given F prime C is 5,000 PSI, Fy is 60 KSI, we have this given frame. The columns are 20 by 20 with 8 number 7s, and the beams are 20 by 36 with 4 number 8s at the bottom. This frame from joint to joint is 24 feet tall, 27 feet wide, and it is braced against sway. The footings, typical, are 24 by 6 feet by 8 feet, and you can see that they're 8 feet in the direction of bending. Required, use the alignment charts to find the K factor. Use table 66311A for effective moments of inertia. Okay, so we can find psi at the top of the column. So we find the sum of all the columns coming into the top of the column over the sum of all the beams coming into the top of the column. Well, this is the top of column joint. I only have one column and I only have one beam going into that joint. So modulus is 57,000 times the square root of 5,000 PSI is 4,031 KSI. I have my moment of inertia is 70% of BH cubed over 12. And for the column, that's 70% of 20 times 20 to the third over 12, 9,333 inches to the fourth. The height of my column is 24 feet or 288 inches. My beams, the moment of inertia of the beam is 35% of BH cubed over 12. So 35% of 20 wide, 36 deep over 12 is 27,216 inches to the fourth. Length of my beam is 27 feet or 324 inches. And we can assume that the columns and beams are all poured with the same concrete. So E is the same for both columns and beams. The modulus is the same modulus. Therefore, psi A is equal to the modulus times I over the length divided by the modulus times I divided by the length of the beams. This comes out 0.386. Psi B at the bottom of the column at the footing. So modulus is the same, 4,031 KSI. I of the column we already found is 9,033 inches to the fourth. Length of the column we already found 288. But for the footing, the moment of inertia of the footing is BH cubed over 12. In this case, H is the planned dimension in the direction of the frame, the 8 feet. So I have 6 times 12 times 8 times 12 to the third over 12, 5,308,400 inches to the fourth. K, as I said, you can use 120 PSI or 0.12 KSI per inch. So I calculate, I have 4 times, notice this one, there's no 4 in this one, it's only in this one. 4 times E times I divided by L of the column over 5.308 million inches to the fourth times 0.12 KSI per inch, and I get 0.82. I can now go to my alignment chart and notice that A is for braced frames and B is for unbraced frames. So I'm going to go to A and I plug in my 0.38 and my 0.82. And where that line between those 2 points crosses this intercept, that's your K value. So as you can see, my K value looks like about 0.69. So it's 0.695, pretty close to 0.7. So this column for practical purposes is considered to be a fixed column. We're going to use a K of 0.70. Okay. Any questions on example 1? All right, you guys ready for a 10-minute break? Is anybody ready for a 10-minute break?
Yeah. Yeah.
All right. So let's rejoin at 6:13. All right, we're back. Okay, ready for example 2. This time, the frame is not braced. So we have 5,000 PSI concrete, 60 KSI steel. Here's our frame. Same 20 by 20, 8 number 7s, 20 by 36, 4 number 8s. So materially, this is the same frame, the same setup, but this time it is an unbraced frame instead of a braced frame. So let's use the alignment charts to find the K factor, and we use table 66311A for our effective moments of inertia. Solution, find psi A at the top of the column. Psi A is equal to, okay, so we have basically the same numbers. Moment of inertia is 9,333, modulus is 4031, length is 288 for the column, and 4031, 27,216 for the beam, over 324 inches for the length of the beam. We get the same 0.386 factor for psi A. Psi B at the foot of the column, these are all the same numbers. We get 0.82 now for the foot of the column. But when we go into our alignment chart, now we're over here in the unbraced frames instead of the brace frame. So if I go from 0.34 to 0.82, let's see, that was 0.386 to 0.82. Now you see that we're over here, and we have a K factor that is just shy of 1.2 now, 1.18. So for a fixed side sway condition, K is theoretically 1. K is suggested at 1.2, which is about the 1.18 that we got. So you can see that from a sway column, you're at 1.2 versus 0.7 for a braced column. So the very same concrete frame, whether it's braced or not, makes a huge difference on these K factors. All right, now that we have our K factors understood, let's get to our slenderness ratio. R is the radius of gyration, and ACI section 6251 allows R to be taken as the square root of I gross over A gross, or you can take it as 30% of H when H is dimension of the rectangular column in direction of loading, or 0.25 times D, where D is the diameter if you have a circular column. These are rules of thumb. I still use the square root of IG over AG just to be sure. So your slenderness ratio is K, the K that we just found from the alignment charts. L, or L sub U, is the unbraced length of the column, divided by R, the radius of gyration. Slenderness effects may be ignored if KL over R is less than or equal to 34 plus 12 times M1 over M2 for braced or non-sway columns, and KL over R has to be less than 40, regardless of M1 over M2. Or if you have a sway column, KL over R has got to be less than 22 before you could ignore it for unbraced or sway columns, right? So the criteria is much stiffer. If you have a sway column, you got to be less than 22 in order to ignore your slenderness effects. But for a brace, you can ignore them if you're less than either of these two, the lesser of these two. Where in these equations, M1 is the smaller end moment, M2 is your larger end moment, and the ratio of M1 to M2 is positive if you have single curvature. Single curvature means that the moments are opposite, right? So they're both trying to bend the column in the same direction. And the ratio of M1 to M2 is negative for double curvature. Double curvature is where the two moments are trying to bend the column in opposite directions, not the same direction. And the moment diagram, you'd have M1 and M2 are adding to each other. And for double curvature, M1 is opposite of M2. So again, the ratio M1 to M2 is positive for single curvature and is negative for double curvature. Okay, moment gradient effect. Per ACI 318 section 66453, we define the C sub M factor as per A or B. And C sub M also appears in steel design. It's the same moment gradient effect. If you've taken a steel design class, this is the same factor. For columns without transverse loads applied between supports, then Cm is equal to 0.6 minus 0.4 M1 over M2. And again, the ratio M1 over M2 is positive for single curvature and negative for double curvature. For columns without or with, for columns with transverse loads, Cm is equal to 1. So the higher Cm is, the more conservative it is. If there are no end moments, then Cm is equal to 1 as well. Cm equal to 1.0 is conservative, and you can always use Cm equal to 1 if you're in doubt as to if you can use something less than 1. Moment magnifier delta. Now we're getting to where we're trying to get to. The magnified delta is based on Euler's equation for buckling load. ACI 318-66442 defines the critical buckling load as P sub C is equal to pi squared EI effective over KL squared, where K is defined previously. For a non-sway, K can be conservatively taken as 1.0, and for a sway column, K is always at least 1.0, but it could be as high as 2.2. EI effective is defined by ACI section 66444 as one of A or B or C. So this is different. Let me back up a second. EI effective is different than what we just talked about, where I of columns is 0.7 and I of beams is 0.35. That was for the purposes of using the alignment charts. For the purposes of Euler's equation, you have to use different values, and it has to be one of these three. So it's either 0.4 ECIG over 1 plus BDNS or 0.2 ECIG plus ESIESE over 1 plus beta DNS or EC times I over 1 plus beta DNS. So they're all bad. They're all kind of a pain in the butt to calculate. Where beta DNS is the ratio of sustained factored load over the total factored load. That's common to all three of these. ISE is the moment of inertia about the centroidal axis of the member. Oh yeah, here. Actually, that's mislabeled. This is the moment of inertia of the steel as here. And then I here is this equation per table 6311B. Yeah, okay, that got a little Okay, so equation A is actually the easiest one because it's 0.4. It's 40% of the modulus of the concrete, the gross area moment of inertia of the concrete, 1 plus beta DNS. Equation B is a little bit more accurate, but that's only 20% of the modulus of the concrete, gross moment of inertia of the concrete, plus this is the modulus of your reinforcing steel times the moment of inertia of the reinforcing steel. So this is mislabeled. No, wait, moment of inertia about the centroidal axis of the member. Oh, okay, no, it's not mislabeled. It's just, it's the area, the moment of inertia of the steel over 1 plus beta DNS. And then this one looks pretty simple, except for that this I is this I, which you got to calculate all this stuff in between. So again, what it boils down to is use the simplest one unless it doesn't work. And then you can try the more complicated ones if it gets you a better answer. Does that make sense? Anybody? Okay, thank you. For non-sway columns, ACI 318 66451 says that the factor design moment M sub C is equal to delta times M2. Remember, M2 was the larger of your factored end moments. So your design moment, M sub C, is delta times M2, where M2 is the larger of each end moment, and there's a minimum M2 that you have to use. The minimum M2 is PU times 0.6 plus 0.03 H, and these are in inches. So that gives you a minimum kip inch value that you have to follow if that is greater than the M2 that you're actually designing to. ACI 318 664 gives the moment magnification factor as dun dun dun. This is what we've been driving at for the last hour. Delta. What is delta? Delta is that CM factor over 1 minus your factored load PU over 0.75 PC. And delta will always be equal to or greater than 1. In other words, if this calcs out to be less than 1, then you just use 1. Okay. Example. F prime C is 4,000, Fy is 60 KSI. Here's our frame again. It's our old buddy with 8 number 7s, 20 by 20 columns, and the beams are 20 by 36 with 4 number 8s. And it's the same frame, only I have a pen support now. The height is 26 feet. The width of the bay is 27 feet. And I have an axial load and an applied moment at the top of this column. That's my setup. The axial load is 800 kips. 550 of that is sustained. The moment is 80 kip feet. What is required is determine if the given column is adequate with the given loading. That's what we want to find. Solution. Firstly, we're going to create a column interaction diagram by calculating and plotting 5 points. Okay, so we're going to basically do another example showing how to calculate 5 points to manually come up with an interaction diagram. So we're going to start with our pure compression, point A. We're going to do 0 tension at the tensile steel. We're going to do our balance condition, our fully yielded condition, and our 0 axial load condition. Okay, so again, why am I doing this? This is probably the most complicated part of column design, are doing these points that you need to do to get that interaction diagram. So I'm doing a different example with different loading, different strength of concrete, different section properties, so that you get another example of how to do these. So for the first case, point A, pure compression. Pure compression, we have to calculate P naught is 0.85 F prime C AG minus AST plus Fy times AST. Your gross concrete is 20 by 20 or 400 inches squared. Your steel is 8 number 7s or 8 times 0.6 inches squared, 4.8 inches squared. So P naught is 0.85 times 4 KSI, 400 minus 4.8 plus 60 KSI times 4.8 for a grand total of 1,632 kips. Pn is equal to 80% of P naught. So that's 80% of 1,632 kips is 1,305 kips. Phi Pn is phi is 0.65 for columns. So 0.65 times 1,305 is 848 kips. And phi P naught, just to give us that point so we know the angle to draw that segment, is 0.65 times P naught is 1,061 kips. And by definition, pure compression, my phi Mn is 0 kip feet. Okay, does this look familiar? You have a problem like this in your homework. Point B is our zero tension point. So with zero tension, C is equal to D, which is equal to 20 minus 2.5 inches. D is 17.5 inches. And zero tension means you have zero strain right at your tensile steel. So that's why C is the same as D in this case. Beta 1 is 0.85. I can look to table 8.7 for 4,000 PSI concrete and get beta 1. A is equal to beta 1 times C, or 0.85 times 17.5 inches, 14.88 inches. So C sub C, the compressive force in the concrete, is 0.85 F prime C AG minus AST prime, which is 0.85 times 4,000 PSI, times AG is that 14.88 times a width of 20, minus the steel in the compression block, which is 2.4 inches, for 1,003.7 kip. C sub S is F prime S times AST prime. Has the compression steel yielded? Don't know. But if I take similar triangles, then the strain in the concrete over C is proportional to the strain in the compression steel over C minus D prime, which is 2.5 inches. So I can solve for epsilon prime S, 17.5 minus 2.5 times 0.003 over 17.5 is 0.0257. That is greater than the yielding strain. Therefore, the compression steel has yielded. Therefore, C sub S, the compressive force in the steel, is F prime S times AST prime, which is 60 KSI times 2.4 inches squared, is 144 kips. Sum the forces in the vertical direction to solve for Pn. Wait, what happened to my tension steel? Anybody remember what happened to my tension steel? Correct. This is defined as zero tension in the tension steel. So by definition, point B, T is equal to 0. So if I sum my forces, all I have on this is the compression in the concrete, compression in the compression steel, and Pn balancing that. So Pn is equal to 1003.7 plus 144. Pn is 1147.7 kips. To find Mn, we're going to sum our moments about the right side edge. Sum your moments equal to 0. So Mn is equal to Pn times h over 2 minus c sub c times a over 2 minus c sub s times d prime. I plug in my values, 1147.7 times 10, which is half of 20, minus 103.7 times a over 2, minus 144 times 2.5, and that all equals 3,649 kip inch, or 304.1 kip feet. Since epsilon sub t is equal to 0, which is less than epsilon y, then phi is still 0.65. So phi Pn is 0.65 Pn. So 0.65 times 1147.7 is 746 kips. Phi Mn is 0.65 times Mn, or 0.65 times 304.1 kip feet is 198 kip feet. Okay, so that was point B. Point C is the balance condition. What's our definition of the balance condition? What does that mean to us? It means that as the concrete crushes at 003, the tensile steel, or the steel the furthest away from the concrete crushing, is just at yield. So by definition, that steel is exactly at yield. So the tensile steel has yielded from similar triangles. Then we can find what C is equal to. So here's my strain diagram. The concrete is at 003. My steel is just at yield at 00207. So I can solve for little c. Little c is equal to d times 003 over 003 plus 00207. That's 10.36 inches. A is equal to beta 1 times c. So 0.85 times 10.36 gives me 8.8 inches. That's the width of my compression block. C sub c then is 0.85 f prime c, ag minus ast prime. So I have 0.85 times 4,000 times 8.8 times the width of the column is 20 minus the steel in this block, which is 2.4 inches squared. And that gives me 590.2 kips. Epsilon prime s, using similar triangles again, is c minus d prime times 003 over c is 00228, which is greater than the yield. So f prime s is 60 ksi again. So c sub s is equal to f prime s ast prime. 60 ksi times 2.4 inches squared is 144 kips. T is not equal to 0 this time. T is equal to the yielding strain, which means that if it yields, the stress is 60. So I also have 144 kips on the tensile steel. So the compression steel and the tension steel balance each other out exactly. The compression steel is in compression 144. The tension steel here is in tension 144. They balance each other exactly. Sum the forces in vertical direction. I have minus Pn plus C sub C plus C sub S minus T. So I have 590.2 plus 144 minus 144 is 590.2 kips. To find M sub n, I sum my moments about this right-hand edge, and I get Pn times H over 2 minus C sub C times A over 2 times C sub S times D prime plus T times D equal to 590.2 times 10 minus 590.2 times 8.8 over 2 minus 144 times 2.5 plus 144 times 17 and a half. That all gives me 5,465 kip inch or 455.4 kip feet. Since epsilon t is equal to epsilon y, phi is equal to 0.65. So 0.65 times Pn is 0.65 times 590.2 is 384. 0.65 times Mn is 0.65 times 335.4 is 296 kip feet. And that's point C. Point D is what happens when the strain is at 0.005. By definition, tensile steel has yielded because 0.005 is greater than 0.00207. From similar triangles, we can solve for C, and we get 6.56 inches. So same diagram, same everything. It's just that the strain in the steel now is at 0.005. So C then is getting smaller. Little a then is also getting smaller. It's 0.85 times 6.56 is 5.58 inches. So C sub C is 0.85 F prime C AG minus AST prime. And we put in A is 5.58 times 20 minus 2.4. I get C sub C now is down to 371.3. Epsilon prime S, this just kind of repeating the process here, but by similar triangles, is 0.00186. Aha, we are now less than yielding. So I can't use 60 KSI. F prime S is 0.00186 times 29,000 is the modulus. Remember, this is Hooke's law. So by Hooke's law, my stress in the steel is 53.84 KSI, not 60. So the force in the steel, C sub S, is F prime S times AST prime. 53.84 times 2.4 inches squared. I'm to 129.2 kips in compression. T is times Fy. Fy times AST, 60 times 2.4 is 144 kips. Sum the forces in a vertical to solve for P. Minus Pn plus C sub C plus C sub S minus T is all equal to 0. So 371 plus 129.2 minus 144 is equal to 356.5 kips. To find Mn, sum the moments about the right side edge. And same equation as before, but now we plug in our most recent values. Pn times 10 minus C sub C times A over 2 minus C sub S times D prime plus T times D gives me 4726 kip inch or 393.8 kip feet. Now epsilon T is equal to or greater than 0.005, so therefore phi has jumped up to 0.9. Phi is always driven by the strain condition of the rebar. So phi Pn is 0.9 Pn or 321 kips. Phi Mn is 0.9 times Mn or 354 kip feet. And lastly, point E. Point E is zero axial load. problem becomes a compression steel beam problem because there's no axial load on it. So rho is equal to 2.4 inches squared over 20 times 17.5 is 0.00686. Rho prime is also 2.4 inches squared over 20 times 17.5 and is also 0.00686. Our familiar equation, if rho minus rho prime is greater than this term, then the compression steel will yield. But rho minus rho prime, they're equal to each other, so rho minus rho prime is equal to 0. Therefore, the compression steel does not yield. So we write out our force equations in terms of C. C sub S is A prime S F prime S, which is 2.4 times 87 KSI times C minus D prime over C, which is 208.8 times C minus 2.5 over C. T is 2.4 times 60 KSI is 144 kips. And C is 0.85 F prime C B A, 0.85 F prime C B beta 1 C. And I can plug in everything except for C. That gives me 57.8 C. Put it all together, I get a quadratic, 57.8 C squared plus 64.8 C minus 522 equals 0. Solve by whatever is your favorite means of solving quadratics, and you get C is equal to 2.5 inches, which means A is beta 1 times C is 2.12 inches. So F prime S is 87 KSI C minus D prime over C, which is 2.5 minus 2.5. So F prime S is equal to exactly 0. There's no stress in the compression steel. Compression steel equals 0. So the tension steel is equal to 2.4 times 60 is 144 kips. Compression is equal to 0.85 F prime C BA, which is 144.3 kips. So I sum my forces. I have 144 times 17.5 plus 144.3 times 2.12 over 2. My moment is 197.3 kip feet. My phi mn is 0.9 times mn, which is 178 kip feet. And by definition, my axial load is equal to 0. This was a pure moment condition. So there it is. That is my completed interaction diagram. This was point A. This was point A in a parentheses where we did phi times P naught. This isn't a real point, but it sets up the slope of this line. Where the slope of this line intersects this horizontal line, that gives you this point here. And then this was point B, point C, D, and E. So there's our interaction diagram. Okay, and now we're going to calculate the amplified moments to compare the loading to the capacity. So this is my capacity chart. The capacity chart, as you notice, has nothing to do with slenderness. So slenderness does not change my capacity by this procedure. What the slenderness is going to do is it's going to amplify my design moments. So we're going to keep the capacity per the section design, and we're going to amplify our design moments and see if they still work within this capacity. Any questions on what we've done so far? Okay, were there any other questions anybody wants to ask about the homework? All right. Well, then I will be available for you for office hours on Thursday, starting at 4 o'clock. And we will pick this up on Thursday at 5 o'clock. Everybody have a good evening. Thank you.
Thank you, Professor. You too.
Thank you.